At midnight, the Supreme Court any person in the U.S. can sue anyone who's help with the abortion and up to $10,000. So it's about all real quote. In effect, the Texas legislature has gifted out to state citizens as bounty hunters, offering them cash prizes for civilly prosecuting their neighbors' medical procedures. Abortion is not the only hot-button issue affecting lawmakers are taking on. Felix Don Gallagher explains new Texas laws that go after voters and
Give me one moment. Okay. All right, good afternoon, everybody. How are y'all doing? Okay, good afternoon. I hope you're all doing well. Welcome to the end of week 3. So let's get started. The link to the warm-up question, I just put it in chat right now. And so what this question deals with is one thing that we're going to be talking about for a part of today are these things called emission scenarios. Basically, what is going to happen to future human carbon footprint activity as far as how many fossil fuels are we going to burn? How much greenhouse gas are we going to pump into the atmosphere? And obviously the implications that has on our environment and on our planet. And so my question here is, what are some of the things that you think could influence that in the future? A good example I could give you for this was COVID-19. Because of the pandemic, many people stopped driving. They didn't drive to work anymore. They stayed home. And that actually greatly reduced a lot of people's individual carbon emissions because they weren't driving anywhere. On the other hand, for other people who weren't driving a whole lot anyway, they're now home, but now their lights are on and they are using more electricity, and therefore they are actually causing more carbon emissions. And so really the question is, what are some other things that you think could affect our emissions in the future? So take a few moments, noodle that, write your answers down on that Google form, and then in about 5 minutes, we'll take a look. And of course, as more people sign on, I will paste the link a few more times. Not to spam your inbox, but just because I want to make sure everybody gets the link. Alrighty, I'll paste that link again. Let's take about another 4 minutes to noodle this question. Let's see where people are at. Okay. All right, so 2 more minutes. And then we'll chit chat about it. All right, let's take 1 more minute and then we'll jump in and talk about it. Alrighty, as always, you can continue writing, but let's take a look and see what people had to say. Looks like everybody responded actually, so the answers kind of flowed in a little bit quicker than in my morning class. So let's take a look and see what people have to say. So what are some factors that could affect how much we emit in the future? Electric cars instead of gas cars. So if we see more electric cars on the road, if we see a bigger demand for electric cars and a reduction in the number of gas cars, that could definitely impact our carbon footprint. Planting more trees, flowers, and so on. More talk about electric cars. Hybrid plug-ins or electric cars, changes in technology and the things like transportation. Airplane emissions, electric cars, solar-powered homes. See what else we have here. Less cars, more public transportation. A possibility of an impending global war may cause an increase in carbon emissions. So I'll actually say that really quickly. So wars can greatly impact how much we emit as a bigger society. When you enter a war, a a big war, such as, another world war, focuses may very likely shift from conservation to the war effort and making sure that that whichever side you're on wins. And that obviously is going to result in more production. That's going to result in more industrialization. And that obviously is going to take a lot of fossil fuels. People aren't driving as much due to COVID lockdowns. And obviously what that's doing is that's actually greatly reducing how much greenhouse gases people are emitting from driving, at least. Now, since they're staying home again, it may actually impact how much they are, how much they're emitting from electricity use, because a good chunk of electricity here in California, about 50% of our electricity comes from the burning of fossil fuels. It's actually more like 45%. But obviously, the more electricity we need, the more fossil fuels we have to burn. New technologies can make other forms of energy more effective and efficient. Yeah, if we were to develop a nuclear fusion reactor, a reactor that is a lot easier to handle and safer than the current process of nuclear fission that we use, that could actually become very safe and a very clean form of energy production. Modes of transportation, food production, clothing production in some ways, smoke from factories, more companies use gas, it'll continue to increase the air pollution. Working from home and studying from home can really help reduce the carbon footprint. Yeah, I actually would say that that's something to really consider. How quickly are we going to jump back into the 9 to 5 commuting to the office sort of lifestyle? Many bosses want to do that, but there's also a lot of pushback from that because working from home has a much lower carbon footprint. And not just that, but it's also less cars on the road, more convenient. Public transportation, so maybe changes in public transportation. Government incentivization, I don't know if I said that word right. Basically, the government incentivizing people. This actually gets to the topic of government policy. Government policy can greatly influence what's going to happen to our carbon emissions in the future. In fact, here in California, we have actually greatly reduced carbon emissions due to government policy. In the late 2000s, 2007 actually, a law was signed into effect, AB 705, that's a different one, AB 23. And basically what that law was, oh gosh, AB 32, I'm so sorry. I don't know why I brain farted right there, but the law was basically put in to reduce our carbon emissions based on the agreements from the Kyoto Accord, which we'll talk about later in this course. And we've actually done it. We've actually seen a massive decrease in carbon emissions in California because of that. So what other governments are going to introduce that kind of legislation or those kind of laws in order to reduce carbon footprints? So you had new programs, reduce zero emission vehicles, mass production of electric powered vehicles, since they use large batteries that have to be replaced over time. Less energy, avoid air travel. So avoiding air travel actually is something that is really being talked about now. We're shifting into an environment where even if people do return to their office, there's going to be a lot less business travel. And that could greatly dictate a lot less planes in the sky and therefore lower carbon emissions. Let's see here. So a lot of people are talking about electric cars, deforestation is a big issue, factory activity. the increase in solar powered things. Let's see here. Wildfires could also greatly impact our carbon footprint. Production of electric cars and things in general. More diseases being released from melting ice caps. This is a pretty complex question. And the reason why I asked it is one of the things that we really need to do now that we have kind of this picture of our Earth warming, we need to be able to figure out what's going to happen next. Why? Because if we can figure out what's going to happen next, we can actually act accordingly and maybe even mitigate and maybe even downright prevent a lot of the warming that's predicted to happen. That being said, there's a lot of unknowns. 2 years ago, nobody knew that a global pandemic was going to ravage our society. 15 years ago, nobody knew that a global recession was going to change the way economics are done. 80 years ago, make sure I do my math right, a little over 80 years ago, nobody knew that we were going to be getting into another world war and that was going to change the balance of power in geopolitics in a rippling effect that still exists to this day. Basically, each one of these sort of either catastrophic events, major political events, economic events, or gradual societal change, each one of these things ultimately has an influence on how much carbon dioxide we as a global community emit, that we as a society emit. And so that's what we're going to be talking about today. We're going to be talking a lot about more recent climate change, what's happened in the last roughly 50 years, and then predictions for the future. And then next week, we're going to start looking into the past. And when I say looking into the past, I'm talking about the way past. I'm talking about 300,000 years ago, 400,000 years ago, 500,000 years ago, pretty much from the very beginning of our Earth's existence 4.5 billion years ago. But for today, we're going to talk about really the most recent developments in climate change and in climate science. So that being said, if I pick up where I left off from last time, oops, sorry. There we go. Let me hit present. And boom. Okay. So if I pick up where I left off from last time, we ended class last time by talking about climate models. And I had mentioned that the concept of a climate model is we want to be able to predict what's going to happen in the future. And we want to be able to predict what's going to happen if we just keep emitting without any care for the environment. Or if we decide as a global society, hey, we need to cut back and we need to cut back significantly. Or if we decide, hey, you know, let's do something in the middle. Well, climate models can then actually help us figure out what the consequences of such actions would be. Basically, what a climate model does is it takes our very complicated planet with all the different moving parts, the different layers of the atmosphere, the land, all of these different things, and it simplifies them in a way that we can experiment with them. Now, the bad news is the simpler the model, the less accurate the prediction is. And when climate models were first developed in the 1970s, they had very little to go off of. We had sunlight, rainfall, and carbon dioxide emissions. And that was pretty much all we had to go off of. And then those things would be fed into the model, and coming out the other end would be a prediction for how temperatures would change. Now, why were the models so primitive? They were primitive for two reasons. One, climate modeling was still a very new thing. we had not yet figured out how to accurately simulate other components of our planet. Things like our ocean currents, things like our land, things like tree life, biology. We really didn't have any ability to accurately model those things yet, to accurately simulate those things yet. But the other bigger reason is the fact that in the 1970s, we had very little computing capabilities. And I think I used this as a demonstration last time, but your smartphone, the little pocket device that we're all addicted to, this thing right here has millions of times the storage capability and thousands of times the processing capability of even the world's most powerful supercomputers in the 1970s. So basically what that's saying is that in the 1970s, we really couldn't make complex models. They had to be very, very simple. However, as we began to improve our technology, and as we began to gain a better understanding of how to accurately simulate different components, we were able to then integrate those into our model. And so eventually we were able to add land surface, and then we were able to add ice. Then we were able to add an ocean. At first it was just a swamp ocean, but eventually it became a legitimate ocean with moving ocean currents. Ocean currents have a big impact on climate as a whole. Don't believe me, I told my morning class this, but don't believe me. Spend a summer day in San Francisco and then spend a summer day in Washington, DC. Pretty close to the same latitude, but very, very, very different weather in the summertime. And the biggest reason, the number one reason, is because the ocean currents that those two cities are next to are very different. We need to be able to simulate that in order to actually construct a reasonable climate system. Well, we eventually were able to do that. Then we were able to add other gases into the atmosphere, not just carbon dioxide, but also methane, which is the second most important greenhouse gas, or volcanic eruptions and how they affect climate. And I'll actually give you an example of that later in class today. And all kinds of other different components. And so as time has gone on, we've been able to make these models more and more and more complex because we now have the computing capability and the understanding of how to simulate these things, and therefore more and more and more accurate. And this brings us to today. Our current climate models, such as the Community Earth Systems model, this is, I always like to tell people this is the Americans' contribution to the Earth, or to the world of climate science, has a lot of different components to it. And I know it's kind of easy to look at that and almost feel like you're a deer in the headlights when you see the insane number of components. Ocean currents, ocean salinity, how salty the ocean is. Believe it or not, that plays a role. Not just clouds, but at what height and how thick are the clouds? How incoming sunlight changes throughout the year due to axial tilt and the distance from the sun. Things that happen on our land surface, including things such as plate tectonics, snow cover, vegetation, how the actual distribution of land and ocean actually change over time due to continental drift. All of these things can now be simulated in a climate model. And so basically what we have done is we have taken our very complex Earth and we've turned it into something that we can tinker with. And then we can feed scenarios into this model and see how it reacts to give us a pretty realistic idea of how our planet will change over time if we continue emitting carbon dioxide, if we have a wake-up call and decide to really significantly cut back, or somewhere in between. And I'll actually talk about those scenarios later in the class. That being said, how do we know that these models are actually true? And for more information on climate models, I have a number of links here that actually explain how climate models work and the history of climate modeling. But how do we know that these climate models are accurate? How do we know that the predictions that they are going to make in the future will actually make sense? What gives a climate model credibility? Take some guesses, type them in chat. Okay, data. So if we have data that we can use, I like that. Accurate data. Now, what would we do with that data? How our prediction matches reality. So basically, I like that, Margarita. Calculated data, the researchers conducting form a hypothesis. I want to go back to this how our prediction matches reality statement. So let me explain what that actually means. So a model is accurate if its prediction comes true. If what happens was accurately predicted by the climate model. It's the same thing with weather forecasting. We consider a weather forecast to be accurate if what it predicted actually happens. A good example of that, last weekend, Hurricane Ida, which unfortunately is still ravaging the east coast of the US. Hurricane Ida was forecast to hit the Louisiana, Mississippi coastline area. And we had a few days of warning to let people know and to get them out of harm's way. We did that. And then Hurricane Ida did hit that region. We predicted where Hurricane Ida was going to go. And then a few days later, that's exactly what the hurricane did. That's called model verification. The forecast that we made ended up coming true. Here's the thing though, when we're talking about climate models, we're not talking about making a prediction for tomorrow or for the day after. We're talking about making a prediction for a decade from now, 2 decades from now, 5 decades from now, a century from now. Now, I don't know about all of you, but even the scientific community does not have a giant crystal ball that they can actually take a look at and see exactly how the world's going to be like in 50 or 100 years. If they did, we wouldn't need climate models. Bingo, I see something in chat right now. So the predicted data equal to or similar to the observed data. Exactly. Basically, what was predicted ended up coming to pass. Well, here's how we do this for climate modeling. We cannot accurately predict the future. Like we can't using a crystal ball or something like that. So we can't get observations from the future. We don't know what's going to happen in the future. So we have nothing to test climate models' future predictions on. But what do we have? We don't know what's happened in the future, but what do we know? What do we know? We do know what's happened in the past. We have observational data collected from the past. Now, here's the thing. These climate models, they don't know the past. Their ability to predict the future is just as good as their ability to predict the past. So what we do is we instead tell the climate model, instead of giving me a forecast for 50 years from now, give us a forecast for 50 years ago. And all you do is you input, like for every climate model, you input a set of what are called initial conditions, and then you hit go. And the model does its work. it makes its prediction, it spits it out on the other end, and that's it. Well, the good news is, since we know what already happened, we can test the model by seeing how well it predicted what happened. This is what is called hindcasting. This is what is called hindcasting. Basically, looking at how a model can reasonably predict the past. If it can reconstruct past climate, then we can say that we have reasonable confidence that it can predict future climate. If it was able to do the past, it can do the future. Because again, it doesn't know the past. We haven't told it the past. We just tell it, okay, make a prediction for this time, and it does so. And then what we do is we compare that prediction to what happened. So let me explain what you're looking at right here. This is actually from my master's thesis, which I did 8 years ago. Can't believe it's been that long. So this is my master's thesis, one of the components of my master's thesis. And here's what I did. I was actually working on a component of the community Earth systems model, specifically the land component. And the land component was given a set of initial conditions called offline data. What I actually did was I compared that model run using those initial conditions to the actual observations taken from a location. Here's what that means. What that means is that these two dashed yellow and dashed green lines are the model predictions that I used. And then the blue line represents actual observations. Actual observations. And the thing that we're looking at is this thing called skin temperature. It's basically the temperature of the ground itself. It's the temperature of the land surface. It's like the temperature of the skin of the earth. So what I did is I did an initial run called an offline run where I had put in a preset set of initial conditions and then hit go. And that model prediction ended up being in yellow. The next thing that I did is using a set of data that was actually collected for this particular location, I actually fed that as the initial condition. Now, this isn't what the model's predicting. These are just the initial conditions that we give the model. These are the input that we give the model. And I put that in there and hit go and let it make a prediction. By doing that, what we're actually doing is we're taking away an error variable and replacing it with an accurate one and seeing what else the model's doing correctly and incorrectly. All of that said, what I found was that this model predicted temperatures pretty well in spring and summer, or sorry, spring and fall, I lied, spring and fall. But actually summer and winter were pretty off. Summer was too warm, winter was too cold. So summer was too warm, winter was too cold. And what we can actually do then is using this, we can then say, okay, one, here's what the model's getting right. And two, here's where the model is, here's where the errors are. We can take those into account in our predictions, and we can also use them to fix the model in the future. So this is how we know that our models work. If they can simulate what's happened in the past, that gives us reasonable trust, reasonable confidence that they can predict what's going to happen in the future. And that's exactly what happens. And I just did one component of one model for one location. So I did a very, very small piece. But right now, as I speak, all around the world, there are thousands of climate scientists doing this exact same thing. They're scrutinizing the hell out of these models, finding out what they're getting wrong and fixing it, so that these models are becoming increasingly more accurate. And because these models are getting increasingly more accurate, that means that our predictions for the future are becoming increasingly more accurate. And I'll actually tell you what those predictions are at the end of class today. So now with this said, climate modeling began in the 70s, and it really kind of took off in earnest in the 80s and 90s. Now, during that same time, the issue of climate change was really starting to take the forefront of society. In the 80s, we started to see drastic warming. That leveling off period that we had seen in the 50s, 60s, and early 70s was over. It was a thing of the past. And now warming has both resumed and it has accelerated. It has gotten worse. So now the Earth is getting hotter and hotter and hotter, faster and faster. And we see it even more so recently. It's just been getting hotter and hotter and hotter. This finally got international attention to the point where something had to be done. So the United Nations, one of the world's largest diplomatic governing bodies, commissioned a group called the Intergovernmental Panel on Climate Change. Basically, this is a panel made up of the world's top scientists from all around the world, taking a look at thousands of pieces of data, or thousands of scientific studies done with trillions of pieces of data, and giving us two things. One, an accurate sense of what's happened, a diagnosis. And two, what may happen next, a prognosis. And these two things are released in what are called IPCC reports. The first IPCC report was released in 1990. And roughly every 5 to 7 years thereafter, the IPCC has released a new report. They released one in 1995, 2001, 2007, 2014, and then they plan to release another report in 2021. They plan to release another report in 2021. And actually, they've actually released that report. That report's actually come out in just the last month. Science teachers like me from all around the world are still digesting it and still kind of getting a sense of what's going on. But really, the situation is more and more dire. Every one of these reports has basically used stronger language and higher confidence that one, we are the main cause of it, and two, if we don't do anything about it, the future looks bleak. So the Earth continued to warm in the 1980s. However, as I alluded to with our warm-up question, there are things that we can't predict that may have major implications, not just on emissions, but on climate as a whole. Case in point, volcanic eruptions. And in 1991, we had a major volcanic eruption. Mount Pinatubo in the Philippines erupted. And it was what is called a VEI 6 eruption. On the scale of 0 to 8. On the scale from 0 to 8, it was a 6. Meaning it was a pretty big eruption. It was pretty high on the scale. This volcano, when it erupted, it shot up over 10 cubic kilometers of ash. Just to give you a sense of how that looks, imagine a cube 6 miles wide, 6 miles deep, and 6 miles tall. A kilometer is about 0.6 miles, so 10 kilometers is about 6 miles. So imagine a cube of ash, 6 miles by 6 miles by 6 miles. That is a lot of ash. That is a tremendous amount of volcanic ash. And this volcanic eruption was so powerful that it hurled most of it into the second layer of our atmosphere known as the stratosphere. Now, unlike the layer that we're in what's called the troposphere. Down here, the weather's very interesting. You've got wind outside, you've got clouds moving around, you get rain, you get cyclones, and all kinds of interesting things down here. The weather in the stratosphere is really, really boring. More boring than this class. It is really, really dull. The winds are barely blowing. And so anything that gets up there can actually be stuck up there for a while. So when something gets into the stratosphere, it could actually stay there for a while before it settles back down to the surface. So all of this volcanic ash, when it made its way up into the stratosphere, it just kind of stayed there. And it instead spread around the entire planet. Just slowly over time, it just drifted and ultimately covered the entire planet. Now, one key, this guy just called my favorite class boring. Well, thank you for saying that this is your favorite class. But no, so what actually happens is one of the key ingredients of volcanic ash, one of the key components, is this chemical called sulfur dioxide. Sulfur dioxide is actually very, very, very reflective. It's like a tiny little mirror. And so when we get all of the sulfur dioxide into our stratosphere, that actually creates basically a giant solar reflector. And so all the sunlight that's coming into the earth, a good bit of it is actually being reflected back out by the sulfur dioxide in this volcanic ash. What that means, not as much sunlight is reaching the surface of the earth, and therefore the earth is actually not getting as warm. This actually resulted in about just a little less than a degree of cooling from 1991 to 1992. So we actually saw a degree of cooling globally. So the global average temperature dropped by about a degree from 1991 to 1992 from the eruption of Mount Pinatubo. And so this is just an example of how one cataclysmic event can give you a short-term change to climate. Now, it's worth noting, though, that all of this dust eventually settles. All of that sulfur dioxide eventually mixed out of our atmosphere. All of the ash eventually settled back down into the surface. And when that happened, warming was able to resume. And we haven't really had any big Pinatubo-style eruptions since. Nothing that cataclysmic. And so the reality is that since Pinatubo, Earth has continued warming. Furthermore, carbon dioxide concentrations, that represents how much carbon dioxide is actually in our atmosphere, all of that continued to go up. So the way that we measure carbon dioxide concentrations is using what is called parts per million, or ppm. If you've done the first homework assignment yet, or if you've taken a look at it, you've seen ppm. It just means parts per million. Basically, if I take 1 million molecules of atmospheric air from all around me, throw them on my desk and count them out, the number of carbon dioxide molecules in that 1 million would be its concentration. And the average global concentration of carbon dioxide reached approximately 400 parts per million for the first time in recorded history in 2013. It's worth mentioning that ever since, it's kept going up. We're at just about 420 now. We're at just about 420 parts per million now. And we just keep going up, and going up. 2016 was the warmest year on record. And I should actually annotate this really quickly. I should actually highlight something. Believe it or not, 2020 actually tied with this. So when the data finally came out for 2020, 2020 actually tied for the warmest year on record. So 2016 and 2020 were the warmest years on record. And here's the scary thing about that. I don't have enough time to go into this, but 2020 was actually a La Nina year. I'm curious, how many of you have ever heard of El Nino before? How many of you have ever heard of El Nino before? Okay, couple of people. Okay. Now, for those of you who've heard of El Nino, you've probably heard it was a storm or something like that, because here in California, when we talk about El Nino, we're usually talking about how it creates stormy weather. But believe it or not, that's actually not the biggest, like, spookiest thing about El Nino, or the main thing about El Nino. El Nino occurs when there's a buildup of warm ocean water. And so El Nino actually has a warming effect on our climate. However, a La Nina is the opposite of El Nino. A La Nina actually has a cooling effect on our climate. La Nina has a cooling effect on our climate. And with 2020 being a La Nina year, meaning that we actually had this big buildup of cooler water, that actually means that 2020 should have been a little bit cooler. However, with all the other factors taken into account, 2020 tied 2016 for the warmest year on record. Just to add on to that, 2017 was the second warmest year on record. 2015 was the third warmest. 2018 was the fourth warmest. 2019 was close to the fifth warmest. Just putting that all into account, the 5 warmest years on record have been the past 5 years. And in fact, 9 of the top 10 warmest years on record have occurred since 2000, with the 10th one being 1999. What that is telling you is that we are seeing more and more record heat. It's only getting warmer and warmer and warmer. It's only getting warmer and warmer and warmer. So with that said, where do we go from here? Like what happens next? What happens next? So where do we go from here? Are we going to keep getting warmer? Is this just going to keep happening and keep happening and keep happening? Well, the IPCC, that group that I talked about, whenever they release a report, I mentioned that they give you 2 things. They give you a diagnosis, what has happened, and a prognosis, what is expected to happen. Well, the IPCC report that came out in 2014, that was their 5th report, said that it was extremely likely that observed warming has been caused by human activity. And more so, that the Earth had warmed between 0.85 and 1.05 degrees Celsius. And in fact, the most recent IPCC report, which again just came out, so I just wanted to put this in there just so you know it, has actually suggested even further warming. They put us at 0.92 to 1.22. What does that mean? That just means that warming is getting more and more intense. And the confidence level with which we are seeing about it being caused by humans is getting higher and higher and higher. Their wording went from somewhat likely to very likely to extremely likely. And in portions of their new report, they even say unequivocal. All of that to say, And I know this is going to be kind of like beating a dead dog in this class, but all of that to say, we're causing it. It's us. We are the main cause of our Earth warming up. And that being said, moving forward, that also means that we are likely to continue to be the main cause of warming. And so we need to be able to predict, how is human activity going to change over the next few years, over the next few decades, over the next century? How is human activity going to change? And that takes us back to the warm-up question that I asked today. What are some of the things that affect how much carbon dioxide we put into the atmosphere? And a lot of you gave really good answers. I saw government incentivization. I saw the dawning of the electric car. Our Tesla is going to become more common. The introduction of new technologies. But there are other things that we can't predict. We can actually give a pretty good prediction of how Tesla technology is taking over the world. We can make pretty good predictions on the advent of hybrid cars and how they are going to continue to sort of take over in the market. We can actually predict those things pretty well because many of those things are planned. For example, here in California, and we'll see if this actually happens, but here in California, the goal, which has been spoken into law by Governor Newsom. I actually like the guy, but no, he actually has given a mandate that by 2035, California would only be selling electric vehicles. That we would only be producing and selling electric vehicles here in California. And the idea is to phase out gasoline vehicles. Now, can we do that by 2035? I think that that's very ambitious, but that actually can have a pretty good impact. Now, that being said, the same guy that spoke this into being is currently up for being recalled. And I know, but my go-karts, well, electric go-karts. Now, here's the good thing though. That doesn't mean that gas cars are going to be illegal. It just means that we're not going to be making any more. What's on the road can stay on the road. We'll still have gas and stuff like that. The idea is to phase it out. But that being said, that same guy who basically, gave that mandate is currently up for recall. And despite the fact that the polls are still showing that he has a good chance that he'll survive it, in 3 weeks, we could have a new governor in California. And if we have a new governor in California, that governor may say, oh yeah, that mandate, that's gone. Let me give you an example of that on a global scale. So in 2015, there was an agreement, an international agreement that was basically agreed upon by all but 2 nations in the entire world. The 2 nations were Nicaragua and Syria. Every other nation in the world agreed to this agreement. It's called the Paris Climate Agreement. The Paris Climate Agreement, its goal is to prevent warming greater than 1.5 degrees Celsius. So to prevent warming from going bigger than 1.5 degrees Celsius. That's the goal of it. And by doing that, countries such as the United States have to do 2 things. We have to, 1, reduce our carbon emissions because we've already industrialized. And 2, other countries that are currently industrializing and currently growing economically and becoming more modernized societies, countries like China and India, countries that are on the upswing, we need to help them industrialize in a way that is much cleaner, that isn't as carbon intensive, that isn't as fossil fuel intensive. We as Americans, we actually had the benefit of being able to industrialize by any means necessary. But now that we have industrialized, we need to now switch over to post-industrial technology, greener technology, and we need to help use that technology for other countries, to allow other countries to use that technology to help them industrialize. Actually sounds kind of like a good thing. However, this is going to cost the United States trillions of dollars. And there's also political implications and social implications to it. Helping out China, for example, that for some is controversial. And I don't want to get into why it's controversial because that gets into a whole intersection that is way beyond the scope of my understanding even. I see things from the science perspective, but there are societal and human rights issues related to that. Well, that agreement was signed in 2015, and the person who signed it for the United States was President Barack Obama. Well, guess what? In 2017, we elected a new president. We elected Donald Trump. One of the first things he did in his first 6 months in the Oval Office, he took us out of the Paris Agreement. He took the United States out of the Paris Agreement. And so the outcome of one election took the second biggest carbon emitter in the world out of the Paris Agreement. And then, when elected into office, Joe Biden, our new president, actually one of the very first things he did on his first day in the Oval Office was put us back into the Paris Agreement. And so now we're back into the Paris Agreement. But think about this, we're the second biggest climate emitter in the world, carbon emitter in the world, and we are the world's largest economy. The success or failure of the Paris Agreement, and therefore the success or failure of global climate initiatives, really does rest in our cooperation, our willingness to do it, our willingness, like our desire to be a part of it. We have to be a part of the solution. But when the outcome of one election really determines that, and we can't predict the outcomes of elections. We learned that the hard way in 2016. We cannot predict the outcomes of elections. What that actually brings us to, and this wasn't meant to be a tangent, but just to bring it back to this emission scenario situation, the fact of the matter is there's a lot of things that we can't accurately model. And so we can create scenarios for them. And so that's what the IPCC has done. It has created a set of what are called emission scenarios that take all kinds of things into account. Are more governments going to pull out of the climate agreement? Are we all going to get back into it? Are we going to stick to it? What is the sociological flavor for all of this? Does society want to do this? All of those things play a role. And so with that being said, the IPCC made 4 emission scenarios. And here are the 4 emission scenarios. These are what are called representative concentration pathways, or RCPs. Representative concentration pathways, or RPCs. And there are 4 of them: 2.6, 4.5, 6, and 8.5. Don't worry so much about the numbers now. I will actually explain what those numbers mean later in the course when we talk about what are called radiative forcings. But for right now, I just want to briefly outline each one of these scenarios. So the RCP 2.6 scenario is sort of a come to enlightenment moment that somehow, virtually right now, The world as a whole has a global wake-up call. Something happens that makes us realize we have to cut back, and we have to cut back now. And so almost immediate reduction of carbon emissions. From that point, we stop emitting as much carbon dioxide. We start cutting back and cutting back and cutting back, maybe even to a point where by the end of the century, we are carbon neutral, meaning that the emissions that we give off are offset by other things. So that's the RCP 2.6 scenario. Personally, I think that scenario is way too optimistic. The fact that a single presidential election can affect the outcome of the United States being in the Paris Climate Agreement, which ultimately affects the success or failure of the agreement, that's kind of scary to think that that could happen. RCP 2.6 is probably not going to happen. The two more likely scenarios are these two middle scenarios. RCP 4.5. Basically, we continue to emit more as a world over the next 20 years as countries such as India and China, the two most populated countries on Earth, continue to industrialize. That causes emissions to continue to rise. However, by 2040, we start to see reductions. The RCP 6 scenario says we'll see them around 2060, and then eventual reductions. And then the RCP 8.5 scenario, this is really what people call the business as usual scenario. This scenario, basically, no carbon reductions. We are just going to keep going the way that we have been going. We're just going to keep going the way we've been going without any real intervention, without any real effort to reduce. We're just going to keep emitting, burning. We don't care. We're just going to keep doing it. Eventually, what causes this to level off is we eventually run out of fossil fuels to burn. We pass peak oil, we run out of stuff to burn. And so then we're kind of forced by hand to go over to post-industrial technology. And that could be a really scary transition if it happens suddenly. Now, that being said, as I mentioned, I think that the RCP 2.6 scenario, this is the best case scenario. But I would say it's almost zero probability. It's not going to happen. But I'll also say that the RCP 8.5 scenario is also very unlikely to happen. And the reason why is because we as a global community are waking up. We are seeing the light. We are realizing that something has to be done about this, and we are acting accordingly. Did you actually know here in the United States, we have already begun reducing our carbon footprint? We emit less now in 2021 than we did in 2005. And much less, and that was happening pre-COVID. So it wasn't just COVID that caused that. So we've actually been reducing here in the United States. The problem is that other countries are now emitting more because they're industrializing. And so that's offsetting that. But those countries care too. They really do. They want us to have a future as well. And so I don't think 8.5 is very likely either. We're going to fall somewhere between RCP 4.5 and RCP 6. Now, really quickly, for the sake of my morning class, somebody in my morning class asked me a question that I thought was really good, but I actually wasn't really educated on it. They asked me about something called the climate alarm clock. Have any of you heard of that, or the climate change clock? Have any of you ever heard of that before? Okay, I've got one person who's raised their hand. This is always the recording that I upload on Canvas. So hopefully my morning class, if anybody watches it, they'll see that I've actually looked it up and have things to say about it now. The climate alarm clock, it was something that was created by a social movement. And basically it was, how many years left do we have before we run out of time to prevent 1.5 degrees of warming, which was what the Paris Agreement set. And basically they said that we need to cut back by 2027 or 2028, one of those, I think 2028. And if we don't do that, we're going to surpass 1.5 degrees Celsius. However, even in the most optimistic predictions, we're still committed to about a degree of additional warming. Meaning we could do nothing now. We could like stop emitting today. And because of all of the stuff that we've already emitted, and the fact that it does take time for it to mix in the atmosphere and it takes time for the atmosphere to respond to it, by 2100, we are already committed to about a degree of warming. The concept of that clock is, what can we do to prevent ourselves from reaching 1.5 degrees? And the idea is that if we don't change anything right now, we will run out of time by 2028. Now, I will say, I think that's more of a sensationalist kind of thing. It's basically giving us a deadline. If we don't do this, then we're going to surpass that 1.5 degrees Celsius. But even in the most optimistic scenario, that 1.5 degrees Celsius is like right in the middle of that. When you actually start looking at the more realistic scenarios, we're looking at 1.7, 2.0, as high as 3.7, depending on which scenario we end up in, or where we end up lying in between these scenarios. We are going to see significant warming. We are going to see significant warming. In fact, the original Paris Agreement was actually going to try to hold warming to 2 degrees. And a few people really pushed for 1.5 and they pulled it off. And I'm not saying that that's unrealistic. I actually think that we really should be shooting for that goal. But the idea is that no matter what, we're committed to a little bit of additional warming. Really, the goal now is to prevent as much future warming as possible, to make this number as small as possible. To make this number as small as possible, with the idea that we, at least as humans, we could probably survive. We could probably live with a world that is 1 to 2 degrees warmer. Now, once you go above that, though, it starts to get really scary. 3 degrees warmer, 4 degrees warmer, 5 degrees warmer, 6 degrees warmer. We actually get into a really scary situation. Now, I know what you're thinking. Okay, so it's 6 degrees warmer outside. Well, first off, these numbers are Celsius. If you converted these to Fahrenheit, these are closer to anywhere between 1.8 to as high as 8 or 9 degrees of warming. Now, it's worth noting that that is not necessarily going to be the case everywhere on Earth. These are global average temperatures. But if you remember, the reason why I said the term global warming is misleading is that these numbers might not be experienced everywhere on Earth in the same manner. Some places may see a lot more warming. Specifically, the North Pole may see a lot more warming. They may see 10, 11, 12 degrees of warming. Other places might see a little less. But these are just the averages. But even in the best case scenario, we are committed to an additional degree of warming. And if we don't do anything, we could be as high as 5.4 degrees of warming. That's a pretty scary number to think about. So really the goal is get ourselves as low on this scale as possible. Get ourselves as low on the scale as possible, so that we can limit warming as much as possible so that we can mitigate as much of the damage as possible. And I believe that that's very possible. I believe that there's still a lot of opportunity to do that. But even though I wouldn't necessarily panic about the climate alarm clock, I would say that the clock is still ticking. But rather than thinking about some set date that we need to do it by, the fact is we need to do it now. We need to start now. All right, that's pretty much it for today. I do have 2 announcements to make really quick. The first one, homework number 1 is still up on Canvas. It's due a week from today. But then I also needed to talk to you all about a dirty 4-letter word that I know strikes fear into the hearts of students. Quiz. Our first quiz is next Thursday. Now, let me explain to you how I do quizzes in this world of COVID-driven Zoom teaching. So the way that I do quizzes in this class is next Thursday, we'll have a normal class. I will actually in class about 15 minutes early. When I in class, the quiz will open up. You will have until Sunday to take it. So you will have until Sunday to take it. Once you start it, you will have until Sunday, or well, not, sorry, no. It is a time quiz. You'll have an hour to take it once you start it. But you'll have until Sunday to start it. The quiz will be made up of 10 multiple choice questions and 1 written question. I've already posted a study guide online. You will be able to use anything you want on it. You can use notes, you can use these slides, you can use the online textbook, you can use anything that you want for it. So the only thing you can't do is work together. So I don't want to see answers floating around on Discord or on Chegg or on anything like that. But other than that, you can use whatever you want. And so there is a study guide up online, and I'll talk more about it next week. With that said, are there any questions, comments, concerns that I can take care of right now? I'll hang out for a moment if anybody needs to type anything in the chat. All right, that's it for today then, everybody. I hope you all have a great weekend, get some rest, enjoy Labor Day on Monday, and I will see you all here on Tuesday. Bye.
Thank you, Professor.
Thank
Take
you.
care, everybody.
Sure, thank you.
Bye. All right, I'm still here if anybody has any questions. Still here if anybody has any questions or needs anything. Otherwise, we are all done for today. And I will see you all on Tuesday. I'll wait a few more seconds before I shut it down.
Professor?
Hey, what's up?
Hey, it's Connor again. I just wanted to let you know I went to go back into the course enrollment for Meteorology 10 and it shows you the class is full. I didn't know if anything changed from this morning because I did check earlier and it showed there were a couple spots available, but if not, it's totally fine. I just wanted to make sure I'm not missing anything.
Oh, did the ad code not work or?
I didn't even try just because I saw that the class was full.
Give it a try. I actually just had somebody drop just earlier today.
Okay. And then one more thing as well, and I wanted to make sure I'm understanding this correctly. Did I already miss like the main drop period for our course, or are you allowed to do that on your end?
No, I actually have to sign something.
Okay.
Yeah, I have to sign something. So what you'll do is you'll get that paperwork, and there's paperwork that you need to fill out, and then you send it to me, and then I'll sign it.
Okay, because the only thing I wanted to clarify too is I'm seeing, is there, I'm sorry to be able to ask you all these questions here, but I just wanted to clarify, thank you. I just wanted to clarify too, is there a different percentage of money I'll get back from the course since I did miss the initial deadline of August 31st of dropping a course, or is that not relevant?
I think since you're swapping and they're both the same units, it shouldn't be relevant.
Okay, perfect. Awesome. Okay, thank you so much. And I'll get that added right now and get that all good to go. Thank you so much. You're the best.
Absolutely. Yeah.
Perfect. Have a good weekend.
You too.
Bye.
Bye. All righty. I'm going to sign off, everybody. Have a great weekend.